the positive x or z direction, it's propagating e to the minus, and it's really gamma z ax. I want to take you through that. That's the, I want to go through this. This is a wave only propagating in the positive z direction. There is a possibility of a wave propagating in the negative z direction would have a plus alpha z. I mean gamma z. What I want to do is focus on some of the basic ideas. If this is the case, then to get the E field as a function of z and t, you would take the real part of this phasor form, and I'll put a little phasor symbol over it. Real part of E, and this would be to the vector phasor times e to the j omega t. Now, you remember me doing this last time? The only thing that does is turn it into a cosine with the argument omega t minus beta z. So this turns it into some E naught plus e to the minus alpha z times cosine of omega t minus beta z in the ax direction. That would be volts per meter. Do you remember me doing this?
Yes.
Everybody? I'm just going through the motions here. We have this in the notes last time. This is real important. So this is a time domain formulation. Now, I'm going to do a few things. First, please watch this. This is omega t minus beta z. So the phase in here would be omega t minus beta z. I've done this before, by the way. Do you all remember this? So how do I get phase velocity? Do you remember I said if you want a wave, like if you're a surfer, and you're at the peak of the wave, and it's moving, the phase of the peak doesn't change. You all with me on this, guys? Right? Yeah. And so what you'll do is we want to figure out what velocity this constant phase is moving at. And we take a change with respect to t of the phase, we set it equal to 0. Since it's a derivative with respect to t, derivative of omega t is with respect to t is just omega, and you get minus beta times dz dt. Now, dz dt is just like dx dt or dy dt. It is a velocity. It's called a phase velocity. So the phase velocity, this is phase velocity, is simply equal to dz dt this way, and that's equal to omega over beta. Now you'll notice that it's positive. If it was a negative going wave, then the argument here would be omega t plus beta z. Do y'all follow me on this one? Omega t plus beta z. If you did the same thing I just did, you would get a phase velocity would have a negative sign to it. You all with me, class, on this one? Mm-hmm. All right. That's phase velocity. Next thing I want to do is get wavelength. So how do you get wavelength? It's the same way we did it back in the day when we did transmission lines.
Omega over 2 pi.
Well, think about this for a second. Always try to draw a mental picture of what we're talking about. Freeze time for a second. Just freeze time and plot this and let alpha be equal to 0. So if you freeze that, you get something like this versus z, right? Mm-hmm. If this is z, this would be the E field in the x direction versus z. And just assume t equals 0 as well. You with me? Just take that. So it's a cosine. What is wavelength? It's always the distance over which the thing repeats itself. It's a period, if you will, in the spatial domain. You with me, class? So how do you get that? Well, if you look here, let omega t equals 0. Please just watch this part. Maybe I should do it over here. So if you let omega t equal 0, then we get the E field as a function of x would be cosine of minus beta z, correct, class? But we know cosine's an even function. It means cosine of minus x is the same thing as cosine of positive x. So I can make this this. Now, how far does it take for this to repeat itself? Any trig function like a sine or cosine? When this goes from 0 to 2 pi, it repeats itself. Do you agree? So that means when beta z is equal to 2 pi, or beta wavelength is 2 pi, That is the wavelength, or it's 2 pi over beta. And that is the definition of wavelength for any propagating phenomenon. Right? Always is. Yeah.
Could we also use the omega to find the frequency,
Sure.
and then use that to find wavelength?
Well, that assumes velocity, though, doesn't it?
Yes.
See, generally wavelength is c over f in free space,
Yes.
or it's the velocity over the frequency in general, but you need the velocity in that case. Here, we just need beta. We don't need a velocity.
But if it's propagating through free space, we can assume c.
That's right.
Okay.
Back to this thing. So that's wavelength, frequency, of course. When we have omega, that's 2 pi f, so you can get f is simply really omega over 2 pi, so that's not hard. I'm going through the things you've seen over and over again from the time of physics and calc probably to your earlier engineering courses. Okay, so we have that. Now we need to do something where we talk about impedance. Remember with when we had transmission lines, we got the characteristic impedance of a line, right? It was the ratio of voltage to current on a given line. Do y'all remember that? We're going to get something like this, but this is going to be the impedance of free space. I want to do it right here. Anybody need to keep writing? You got it? Everybody got this? I want to just erase this. And I'm only doing this for a positive going wave, but the negative going wave will have the same basic shape. I mean, it'll have the same characteristics, and I'll explain it in a second. So if we have a wave propagating in the positive z direction, and its E field is in the x component like this, then I can say that this E field is equal to some E naught e to the minus j gamma z in the ax direction, right? Now after that, here's what happens. If I think about this, I want the ratio of E to H. And I know, by the way, I don't know if you remember this, but when I was doing all this, I came up with an equation that was del squared of E, you don't need to write this down, minus gamma squared E equals 0. That was, I had two of the curl equations, I got this. Then I made the assumption the E field had only an x component, was propagating only in the z direction. And I found from there that the E field itself was equal to some E naught plus e to the minus gamma z plus E naught minus e to the plus gamma z. And of course, this is in the ax direction. Now, I'm kind of going through this quick. You don't need to write that down, but you remember, right? What we could have done also, and you don't need to write this down, just listen to me. Let me work here on this one. What we could have done is got this. You could have got the curl of H. I'm going to write these down. You don't need to write it. Is equal to sigma plus j omega epsilon E. And curl of E is equal to minus j omega mu times H, right? Now, a thing you can do is take another curl of this one. We took a double curl of this, and we got an equation just for E. If we take another curl of this one, we'll get curl of H equal to, and then it's going to be sigma plus j omega epsilon times curl of E, which is this. So it's going to be times minus j omega mu times H. Then you can call, of course, gamma is equal to the square root of really j omega mu times sigma plus j omega epsilon. Gamma is alpha plus j beta. And I can go ahead and take this and break it up, and I have gradient of divergence of H minus del squared of H is equal to, and then this becomes minus gamma squared of h. Does everybody follow me? I'm just going through the motions. But here is an interesting fact. Without making any assumptions, what is divergence of h? Well, it's really one. It's divergence of mu b, right? H is mu, or I should say, b is mu h. So it's h is b over mu. My bad. So it's really, if mu is not spatially dependent, it's 1 over divergence of b. Do you remember what this is and why? Anybody? It's a very important thing. What's the divergence of D back in electrostatics? Anybody?
Rho v.
Rho v. What does that indicate? A charge density, right?
So it's 0.
Because there is no singular magnetic charge. It's always a dipole. It means there's always a plus and minus so far, just basically an angstrom apart, even less. All right, so this is 0 by definition, makes this go away. It's 0. That's the bottom line, right? Now, what does that mean? So I have an equation where I have del squared of h minus gamma squared of h equals 0. Go with me. That equation will have, again, 2 components, just like that one does. If we assume it's propagating in the z direction, plus or minus z, you're going to get an h field from this. It'll be equal to some h0 positive, and it'll be e to the minus gamma z. I'm going to just show you, put it down here. It'll be in the ay direction, plus it'll be h0 minus e to the plus gamma z in the ay direction. And this is a wave traveling in the minus z direction. This is a wave traveling in the plus z direction. I'm just putting this down for completeness. It's in the book, or at least he alludes to it. Everybody with me on this? This is the H field. Now, if you come over here and we just worry about E field propagating in the positive z direction, so this is only phase velocity is plus z directed. When we come down here, and I know the curl of E here is equal to minus j omega mu times h, based on Maxwell's equations. Does everybody agree with that? I'm just stating the obvious, right? So what is the curl of E? I'm going to do the matrix, or that determinant form. So when I take curl of E in general, that's equal to a determinant, and here it's ax, ay, az, and then it's going to be ddx, ddy, ddz, and here it's going to be ex. Now we know ey is 0, there is 0, right? It's only has an x component. Do you agree with that, everyone? As a matter of fact, if I put in the value for e of x in that determinant, look at the back of look at the back cover of the book, you'll see this down there for the curl and Cartesian. This is actually going to be E naught e to the minus gamma z. Can you all see that? I'll erase this. Hope you can. Do you all agree with that? All right. So, what is this going to be? The curl of E? Well, take a look. Now remember, the E field, I said I determined, more or less I specified it's polarized in the x direction, it's propagating in the z, right? When you do that, what happens? Well, you get ax times ddy, oh, I'm sorry. Here you're going to get ay times ddz of this, so it's going to be ay times ddz of e naught plus e to the minus gamma z. Can you all follow me? I'm just going down here. ay ddz of this, right? Yeah. Minus this. Well, what is ddy of something that's a function of z alone?
0.
0. So it's just this, and this means it becomes When I take a derivative of this, I get E naught, then I get minus gamma here, there's a minus gamma here, and I get e to the minus gamma z in the AY direction. That would be the curl of E. I come over to the other side, and I know what curl of E is. This actually, I'll do it right here. Can you all see this with me? So I'll put that in here, and I get minus gamma E naught times e to the minus j gamma z. It's in the AY direction. Is equal to minus j omega mu h. And one thing you can see from this by looking at h itself will be given as, and this is for the positive going portion of this, h will be given as E naught gamma over j omega mu. I hope you can see this, right? And it's going to be times e to the minus, I shouldn't say j, it's just minus over minus gamma z ay. Now, the only thing I've done here is I've divided by minus j omega. The minus signs cancel, by the way, so you get gamma E naught, and that's just the magnitude, e to the minus gamma z over j omega mu ay. Do you all follow me on this? I'm about to modify this. I want you to be attentive here. This is important. So if I take a look at this carefully, I can say I have E naught plus times e to the minus gamma z ay, and then it's divided by j omega mu over sigma, over gamma. Now, gamma is the propagation constant. So I want to talk about that. If I have j omega mu over, and this would be square root of j omega mu times sigma plus j omega epsilon. I'm going to give you a second. We're going to I'll tell you what the term is. It's called the intrinsic impedance right here. Of the media. The units are ohms. But what do you notice happening? Just take a look at this. I hope you can read my writing. This is j omega mu, but there's a square root of j omega mu right down there. Do you all see this? So what you can do is write this as square root of j omega mu over sigma plus j omega epsilon. And this is called the intrinsic impedance. It's usually given as some magnitude of the intrinsic impedance, e to the j phase angle of the intrinsic impedance. Now, a couple of things to know. Is everybody with me on this part? What this does is really give us the ratio of E naught to H naught. And here's what I mean by this. If you look here at this part, here's what I'm really saying. When I look at this, I have an H field.
I have a question real quick. Does that say J theta in?
J what?
Theta in?
This?
Yes.
That, it's just the angle of this thing. It's magnitude of this thing and angle of this.
Okay.
This is actually epsilon. This is theta. All right. Now, follow me on this part. H in general is some H naught for a wave where E is in the Z direction, in the X direction, propagating the Z direction. It's some H naught. We call it a plus. It's e to the minus gamma z in the AY direction. But it can be rendered as E naught plus over eta e to the minus e to the minus gamma z ay. And it means that H naught is equal to E naught over eta, and this is magnitude here. And therefore they say that really the ratio of E naught to H naught for positive going waves is simply eta. And that's what you'll see. Now I've got another comment. Remember, those are for waves moving in the positive z direction. Y'all with me? We'll do the problems and a lot of this is going to be applied. Everybody with me on this? Now something real important though. If a wave is moving in the opposite direction, I put it here. If you have a wave moving in the minus z direction, so the wrong way you might say, or in the opposite direction, then the ratio of E naught negative to H naught negative will be minus that intrinsic impedance, or it'll be minus the square root of j omega mu over sigma plus j omega epsilon. The reason the minus comes about is because when you do the curl V over here, and you got a minus traveling wave, the gamma here is a positive. So you're going to get an opposite sign for intrinsic impedance. And you're going to see when I apply this, it'll make a little more sense. Are you all with me on this kind of? Mm-hmm. All right. Now we do problems. So I'm going to erase all this, and we're going to apply all this to problems. So go ahead. Which one would you like me to start?
Let's just go in order. 5.29.
All right, go ahead.
Magnetic field propagating in free space is given by h of z, comma t.
H, comma, z, comma, t equal
20 sine pi times 10 to the 8 t plus beta z in the ax direction.
Okay, free space or?
Yes, free space. Find frequency. The beta, that's the wave number, right?
Yeah.
Beta, wavelength.
They want frequency F, they want beta, what else?
Wavelength.
Wavelength, go ahead.
And E.
And E, all right. So, this is a sine. Most of the time, they're cosine. They should be cosine in general. But what's the relationship between a sine and a cosine?
The 90-degree shift.
Mm-hmm. So, if you take well, think about this. This is a sine wave versus theta. This would be sine of theta versus theta. A cosine wave is like this. Not very well, but something like that.
It shifted right 90 degrees. The cosine wave shifts right 90 degrees to the side.
So if you take the sine minus 90, you get cosine. Do y'all agree with that? Right there. So this is equal to 20 times cosine of pi times 10 to the 8. You don't have to do this. T plus beta, and it's going to be, it's a t there, and it's going to be minus pi over 2 radians, and it's still AX. Do y'all agree with this? Now that's, you don't have to do it this way, but now it makes a little more sense. Do y'all follow me? There's a phase angle in there. Okay? What is this?
Omega.
Omega is always the coefficient of t. With me?
Yep.
And that is what? 2 pi f, right? So that means R omega is pi times 10 to the 8th, right? It means F is going to be 1/2 times pi, times 10 to the 8th, or it's really 5 times 10 to the 7th, or 50 megahertz. space. Y'all agree with that? Just do the math on this. It's not tricky. With me?
Yep.
All right. Next for beta. I told you beta is always what? Beta is 2 pi over lambda.
Yep.
Right? If you wanted to do it that way. Now this is free space, right?
Mm-hmm.
We could go ahead. They don't give us beta, right?
Nope, and then we don't get VP either.
That's a, well, free space we do.
Oh well, yeah, we get C.
So now we know in free space, V phase is equal to omega over beta, right? And it's equal to C, because he says free space. Free space is a vacuum. It's moving at the speed of light. Does everybody follow me?
Yes.
With me? All right, we've got omega, we've got C. Beta is what? Well, beta is going to be omega divided by C, isn't it, class? And what is that? Omega is...
Pi times 10 to the 8th. No, pi times 10 to the 8th.
Sorry. So you can help me with this. Pi times 10 to the 8 over C, which is 3 times 10 to the 8.
So it's pi over 3.
So it's pi over 3 radians. Right. What's alpha, by the way?
I don't do that.
Free space. Think about what gamma is, and you're going to see it in a second. What is gamma? It's equal to alpha plus j beta, and it's equal to square root of j omega mu times sigma plus j omega epsilon, right? Well, just think about this. If it is free space, what is the value of sigma by definition? How much conductivity is there in free space? None, right? It's zero. There's nothing to conduct anything. It's zero. There's no mass. So if there's no mass, what do you see here? I got j omega mu times j omega epsilon is what? That's j omega times square root of mu epsilon, right? Plus 0. Alpha is 0, right? This right here will be alpha. It's 0. Do you agree with that, everyone?
Yes.
All right, now, based on that, if alpha is 0, and I'm doing this just to make sure everybody's on the same page as I am here. Now, what next? Well, if we've got beta, what is lambda? 2 pi over beta, right? That's 2 pi over pi divided by 3, right? Or it's really 6 meters, is that right?
Yep.
I think. What else? Oh, they want E. So how do we get E? Now this I want you to pay attention to. And I'm going to tell you a couple ways you can do this. He did this on purpose to cause you to think. Go over here for a second. Stop. 1 second. I want to make sure everybody sees this. Y'all follow me that this right here is the H. I'm going to show you a trick. That's H is the function of ZT. Correct, class? Now, this we haven't covered yet. I want you to watch this. This is a trick. So I can put this in the phasor domain. Now listen, in the phasor domain, H vector phasor, and this is for a wave traveling actually in the minus Z direction, right? If you look at this, this is equal to 20. Is it 20 milliamps or 20 amps?
It's just 20 amps per meter.
20 amps per meter squared. Now, the next thing you've got to do is we know what beta is, right?
Wouldn't it be beta Z?
I mean, sorry, beta Z. You're right. Beta Z. My bad. We know what beta is, right?
Yes.
Now, it's going in the negative Z direction, right? Which means when there's alpha 0, it's going to be e to the plus j beta times Z. Now, beta we have as, what is it? Pi over 3. Just leave beta equal to pi over 3 here. Y'all with me? It's positive, right? Because it's going in the negative Z direction. Y'all see that?
Okay, I have 2 questions. One's not my question. You dropped the pi over 2.
I'm going to put it in.
Wouldn't it be, it'd be minus 2?
What?
It'd be minus pi over 2, right? Because it shifts.
Yes. Minus.
But the question I had was, how do we know it's propagating in the minus Z direction?
Remember, the key was coefficient of beta. If it was minus, it's going in the positive direction, it's multiplying z. If it was minus beta z, it's positive z direction. If it was plus beta z,
That makes sense.
it's minus
That
z
makes
direction. Remember I showed you how to calculate phase velocity by saying all this stuff's equal to a phase, taking a derivative? If this is minus, you'll get a dz dt that's positive. If that is plus, it'll be a dz dt that's minus. All right, next, I have to take care of this phase angle, and I'm gonna. So it'll be e to the minus j pi over 2. This phase angle will have no bearing on most of the stuff. And you suppress frequency, it's in the ax direction. Now that's the h field in the phasor domain from this. All right, can everybody follow me on this?
Yes.
Now, what I'm about to show you is important. You could, if you wanted the E field, I'll do it over here. I'm going to show you, this works all the time, but I'm going to show you a trick. Now, what I'm about to show you, this will work no matter what. If you wanted the actual value of the E field, well, you could take, and you realize that if we wanted the E field, that curl of H is equal to sigma plus j omega epsilon times E. So if you wanted the E field, technically, you could say, well, I could take the curl of H, I have H, and I could divide it by sigma plus j omega epsilon, right? Y'all with me on this? That's just using the definition of curl of H, or constant frequency, so that'll get you the E field, but it's a curl, and we don't like curls, so we don't need to do it. So here's a real trick that you'll thank me for. It's in his book, but it's not in this section, I don't believe. I'm going to put it here. I'd write this down. This is only for plane wave propagation. So it doesn't work otherwise. So the relationship between E and H is this. If you want the H field and you have the E field, and this is in the phasor domain, you want the H field, you can take 1 over the intrinsic impedance of that media times a unit, it does the curl basically, times a unit vector in the direction of propagation, and cross it with E, and you can get the H field. Now, here, AP is a unit vector in direction of propagation. And, you get that by investigating the arguments there, or they can be given explicitly. Eta is the intrinsic impedance. Of the media. And for this equation, and for the one I'm about to give you, eta is always defined as j omega mu over sigma plus j omega epsilon. So that's how it's always defined. I just want you to follow me. Is everybody with me on this? Now, the other part of that, and I'm going to put it right here. Remember, this is only for plane wave propagation, but it works all the time. If you wanted the E field and you had the H field, it is equal to minus eta, the intrinsic impedance, times the unit vector in the direction of propagation, crossed into H. Always. I'm going to do this, and you're going to get this over and over again. One other thing that you always remember, E crossed H is the direction of propagation, always. And it's also the actual power density. So if you take a look at the average power density, this is going to be average power density. PAVE, it's equal to 1/2 the real part of E crossed into H conjugated. Now, y'all remember how you did V cross I conjugate? Did you have that in circuits for power? It's 1/2 the real part if E cross, or V cross I conjugate. The conjugates get rid of the imaginary component. This is the actual power density, and it would be in watts per meter squared. Now, this is all assuming sinusoidal notation and stuff like this. I'm going to get back to this problem in a second. I'm not going to eat lunch. Or if I'm going to eat lunch, it's going to be a lot less. All right, back to this thing. Now, we were asked for the E field, we have the H field for a plane wave propagator, right? This is what's given, right? Watch me on this one. So we want the E field, we want this. It's free space. So in free space, or in a vacuum, same thing as a vacuum, eta is just eta naught. And if you think about the definition for intrinsic impedance, look at this. If this is the definition of intrinsic impedance and you're in free space, well, sigma 0, right? The J and omegas cancel, you get the square root of mu over epsilon. Please write this down, make sure you know it. This, the intrinsic impedance in free space, is equal to square root of mu over epsilon, or mu naught epsilon naught. That's the square root over 4 pi times 10 to the minus 7 over, and you can write this as 1 over 36 pi times 10 to the minus 9. Do you all remember that? You can write it as 8.854 times 10 to the minus 12, or you can have 1 over 36 pi times 10 to the minus 9 epsilon naught. And what is that? That's exactly 120 pi ohms, or about 377 ohms. Can you all see that, class? Take a look at that. The pi squareds come out as pi. Then I have 36 times 4, right? Square root of that. And then I have, that's 12, that's 144, that's square root of 144 is 12. Then I have 10, yes, squared, that's going to bring out a 10, or 100, and the square root of 100 is 10, so that's about, it's 120 pi ohms. Y'all with me?
Yes.
Everybody catch up on this. I know I'm talking kind of fast. Y'all, is everybody following me on this? You good with this? Sure. All right, now let's do this. Let's go ahead and get the E field. So for our problem, we have eta is eta naught equal to 120 pi ohms. What's the direction of propagation? A unit vector in the direction of propagation?
It would be AZ.
Minus.
Minus AZ?
Remember, it's going in the negative direction.
Because beta is positive.
Yeah, it's going in the negative direction. Y'all follow me in this class? So it's minus AZ. Now just turn the crank on this. So that means my E field that I would get, we're going to turn it back into a sine, it probably does, is going to be equal to eta, or it's minus 120 pi, and then unit vector in the direction of propagation is minus AZ crossed into the H field, and the H field is that, so it's crossed into, that's a cross product, 20 e to the j beta z times e to the minus j pi over 2 ax, right? Remember, that's a cross product right there.
Bless you.
Bless you. You all good with that, class? That's just good. What do you see happening here? How about right here? Minus and minus goes to plus, right? Next, we got 120 times 20. That's really what? 2,400 pi? Isn't it?
Yep.
And then we have e to the j beta z. Beta, of course, is pi over 3. We've got it there. Then we've got that phase angle business, e to the minus j pi over 2. Then I have az, right, crossing ax is y. Y'all agree with that? And that's in the I mean, this is in the phasor domain, right? How do I get it in the time domain?
We just go back.
You multiply, technically, you multiply this by e to the j omega t, and then take the real part, right? But I'll show you what happens. Let me do that here. Then I'll erase this whole board. Go sequentially. So, in general, if I want the E field in the time domain as a function of zt, it would be the real part of e to the j omega t times a phasor domain term, all that junk. Okay? I'm just going to leave it as E phase, and you're going to see this in a second. Y'all agree with that? Now, what's really going to happen is that e to the j omega t, when it multiplies this, the only thing it's really going to affect is this. You can get a single coefficient, you have e to the j beta z minus pi over 2, right? Times e to the j omega t means it's e to the j omega t, right, plus beta z minus pi over 2. When I take the real part of that, I get a cosine, right? So at the end of the day, what I get is this. I'll get an E field as a function of z and t being equal to 2400 pi, right? Then it would be cosine of omega t, which I'm just going to leave it as omega t plus beta z, and it's going to be minus the phase angle of pi over 2, and it's going to be in the y direction, right? And that would be volts per meter. Now, if you wanted to, you could put it back to a sine, right? We could get rid of the pi over 2, the minus pi over 2, and just turn it into a sine. So you could put it, if you want, as 2400 pi sine of omega t plus beta z ay. And that, in fact, could be, what answer does he have for this one, by the way? Do you have the answers?
I don't know. He has 7.5 sine, and then
7.5.
Yeah.
pi comes into the 8t plus pi over 3.
Say that again.
This one right here.
That's kV. Do me a favor, take 2400 pi, just multiply it out.
It's 753.
Yeah, that's it then.
kV?
Yep. So
That's what
it's
you-
about
That is.
7.5
That's
kilowatts.
what he has.
Yeah, that's basically it. Y'all follow me? And that's how you'd get it, but that's the whole 9 yards. Now those two tricks I put down here and here are in your book. Let me show you where they are in your book. That way, it's, I think, in a forward chapter, but I want to tell you that that is a neat little trick for any plane wave propagation. And it saves a lot of manipulation. I'm not a real fan of curl stuff if I don't have to do it. I did, this is in chapter 6, but here it is. It's on the bottom page 327. Y'all hear me on that? Those are two equations that are indispensable for propagating electromagnetic field theory. You got them? If you have your book, 327, right?
327.
Okay, so underline that, start, whatever it takes. Let's do another one, and this stuff is, I mean, the problem's in chapter 5 at the end. He wants you to brutally go through the curls, and I don't think it's wise to just have you guys bludgeon yourself. And so you can appreciate the fact you don't have to do them in chapter 6. You can do them, but my gosh, it's a pain. Especially when you get, cylindrical or spherical coordinate systems, you got curls, that wouldn't carry out. This is plane wave propagation. What I'm showing you makes life easy. So what's the next thing? Does that make sense to everybody? Okay. No? Just help me out. What doesn't make sense? Let's try that. No, it's following. A lot of math. Actually, it's a lot of symbols. The math is trivial once you see it. All right, which one we got now?
Let's do 530. I think that's the next one you have.
530?
Yep.
Go ahead.
You're all
I'm just tired. I am too.
a 10 megahertz magnetic field travels
All right, hold it. F equals 10 megahertz. Okay, go ahead.
travels in a fluid for which the propagation velocity is 1 times 10 to the 8th meters
So
per
it's
second.
10 to the 8th meters per second. A lot slower than the speed of light.
Initially, we have h at 0, 0 equal to 2 in the AX direction,
Amps per meter.
amps per meter, yeah. The amplitude drops to 1 amp per meter after the wave travels 5 meters in the y direction.
All right, so here's Y. It's going in the Y direction.
Ye-
Here, we're gonna just take a look at this. This is gonna be, it's 2 amps per meter at 0, so this is H, just call it magnitude of H. It's 2 amps per meter at 0, and it goes down to 1 amp per meter at 5 meters?
Yeah, 5 meters
All right, so at 5 meters.
in the y direction.
And what do they want to know? We're gonna do this one
They
together.
want to find the general expression for the wave and find the instantaneous expression for the E field.
All right. Now, just take a look at this. Ask yourself how you do that. Well, you can tell one thing, it's attenuating. What he's showing you is the magnitude. I'm showing you the magnitude of the electric field. It's not in the time domain. It's a phasor magnitude. You all follow me? So it's propagating in a positive y direction. Now the H field itself, therefore, it could be in either the z or x direction. He gives it in the x direction. But this will be equal to some h naught, that's just the magnitude t equals 0. And then forget cosine, we're going to phasor. You don't need to do it in the time domain here because it's all magnitude. Then he's going to be e to the minus gamma. Well, gamma is alpha z times e to the minus j beta z, right? In the a, and this is going to, y, pardon, alpha y, beta y in the x direction, right? That would be in the phasor form. Y'all follow me? I'll show you some stuff. Now, this is new to you guys, so just be attentive here. So, whenever you see something like this, I got alpha, I got beta, he gives me the attenuation rate, right? Follow me? Watch
Yes.
this. So here, I know when I look at this, then he gives me the frequency, right? So he gives me a frequency. When I look at this, I know that H naught right here, whatever the value is here, which is 2, maybe I should use 2. 2 here is got to be equal to the H naught or 2. That's H naught is here at 0, 0, it's 2. But at 5, it goes down to 5. So it's got to be equal to e to the minus alpha times 5. You all follow me in that? That's magnitude, right? Normally, the H field has this expression in the phasor domain. If it's positive, if it's going in the y direction, it would be some H naught, and it would be e to the minus alpha y, e to the minus j, beta y, right? Can you all follow me in this? It would be in, of course, 8x. This is the phasor form. Now, if I take the magnitude of the H field right here, that's simply going to be H naught right here, e to the minus alpha y. The e to the minus j beta y. E to the minus j beta is e to the some angle, e to the j anything. The magnitude, that's always 1. Can you all follow me? With me on this? All right, so I can get alpha, can't I?
So wait, I have a question.
Yeah.
So at so h of 0, did we
They
just find h naught?
H naught is given at 0, 0. It's simply 2, right?
Okay, yeah, and it does, h naught is constant no matter where we
No,
are.
it's time varying, but we're just looking at the magnitude. When we have a phasor really is the magnitude of the stuff. It does have a phase, but if we just take the magnitude of that, it's magnitude versus position. Y'all follow me? Can you follow me, Gracie?
Yeah, that makes sense.
Now watch this. How do we get alpha? Well, that means it's 1 is equal to e to the minus alpha times 5, right? Take the natural log of both
Oh,
sides.
and also it's
Huh?
it's 1 at 0,
Oh, I'm
5,
sorry.
5.
This is, yeah, but what it amounts to, yeah, this is 1.
So is H not 2 because it's
2 is at 0.
Yep.
All right, so that's
Okay.
this. And then we take e to the minus alpha times 5 meters, and we get the value of alpha. That's what I should. You with me on this, class? Yeah.
And also, why did the beta term go?
What's the magnitude of e to the j
Is
anything?
the magnitude just 1?
E to the j of anything, magnitude is 1, isn't it? Isn't that just 1 at an angle?
Mhm. Yeah.
All right, take the magnitude of it. The
Yep.
only thing that matters is the alpha, the real part.
Oh, yes, yes. Okay, that makes sense. Yes, yes, yes.
Everybody with me? Okay, so what is this going to be? Now I have 1/2 equals to e to the minus 5 alpha. Natural log of 1/2 is equal to minus 5 alpha, or alpha is equal to natural log of 1/2 divided by minus 5. I don't know what that is. Can you give that to me?
Negative 0.138.
Minus, say that again? Can't be minus.
Well, 0.138.
Yeah. 0.138. Is that, does he have an answer for this?
Yeah, that's it.
Okay. What else does he ask? He wants an expression for H, is that right? Well,
E, expression for E.
and this one is E? That's okay. We're good. Is that right?
Yes.
Now that we have alpha, think about this. What is gamma? Well, gamma is equal to square root of j omega mu, right? Times sigma plus j omega epsilon. And we know, if we look at this, we get alpha plus j beta, right?
Mhm. Yes, yes, yes.
Okay, we got alpha. Right? When he says this, now read that problem again. Does he say, I'm just curious about one thing. Does he say it's magnetic?
Yes, a magnetic field.
No. He says the medium magnetic or not? Does it have mu equal mu naught?
There is no, no. It's in a fluid.
Fluid doesn't matter. What problem is it? I mean, read the whole thing one more time. Sorry.
A 10 megahertz magnetic field travels in a fluid with the propagation velocity is 10 to the 8th meters per second. Initially, we have h0 of 0 is 2ax. The amplitude drops to 1 after the wave travels 5 meters into the y direction. Find the general expression of this wave. Find the instantaneous expression for E.
So, this is a little bit, he's doing something that he doesn't quite give you everything, and here's why. Now, I'm assuming he's saying that it's non-magnetic. Because if you look at this equation, we've got alpha, but here I've got omega. I don't have mu, sigma, or epsilon. Y'all follow me? I need either to know that it's non-magnetic, and this itself would be mu naught, and then
You can solve for the other two.
because you can't solve this thing without an assumption. Now, if you look at this, remember gamma itself is going to be equal to square root of j omega mu times sigma plus j omega epsilon. Here we know that's equal to alpha, and our alpha was, I forgot what it is, 138? Correct.
Well, yeah, 0.139. 0.139.
0.139 plus, it's going to be j beta, right? We know something else too. We know when we take the derivative, look at this, when we take for phase velocity, that's really omega over beta, right? Just bear with me. You all with me on this?
Yes.
So we have phase velocity, he gave it to me as 10 to the 8th meters per second. If I want beta, I can say it's going to be omega over 10 to the 8th. Y'all agree here? I'm just manipulating things. Omega is 2 pi f. So beta is 2 pi f, and f is 10 megahertz?
Yep.
So it's 10 to the 7th over 10 to the 8th. So what is that, 2 pi over 10?
Which is pi over 5.
Then what is that? What is pi over 5? 0.6 something, isn't that right? 0.
It's 0.628.
All right, that would be radians per meter. Now we've got beta. What else does he want? You got alpha and beta.
He just wants E.
Okay, let's get the H field, then we'll get the E field. Now again, there's some leeway here because he didn't give us an angle. He just said this is the magnitude difference. So I'm going to do that over here. First, I'm going to write an equation for the H field, and then I'm going to get the E field. All right. All right, work with me on this one, please. Be a pen. This will help you so much what I'm about to do. I can't put it really enough emphasis on. So I know the H field, well, it's got a magnitude of 2, right? Amps per meter. That's 0, right?
Yep.
Then it's got an attenuation, e to the minus, I'm going to leave it as alpha. We know alpha is whatever it is, 0.139 of alpha y, right? Then it's got e to the minus j beta y. We've got alpha and beta, correct? It's in the AX direction, right? Watch now. Y'all agree with that? I'm not putting amps per meter, but I think everybody follows me. You with me, class?
Yes.
Let's get the E field. Think back over, I erased what I showed you over there. E field is 1 over eta, unit vector in the direction of propagation crossed into, I'm sorry, just the H field. E field. The E field is minus eta, unit vector in the direction of propagation, crossed into the H field, correct? Okay. How do I get eta? I want you to think about this. We've got alpha, we got beta, right? Well, if you look at this, what is eta? Square root of j omega mu over sigma plus j omega epsilon, right? We need eta, don't we?
Yes.
First, you all agree with this? Now, I guess you can do this a couple of different ways. I'm looking at this. I wish you could set the non-magnetic. But since, look, we have, yeah, just bear with me. I'm going to erase this and just show you what we got. I don't know if he does it this way, but what I need is eta to go here. I need that if I'm going to use that equation. I got H, I got the direction of propagation, I need eta. If I look at this, I have gamma is equal to alpha plus j beta, and we know we've got that. So gamma squared is equal to alpha plus j beta squared. Just bear with me on this. You agree with that?
Yes.
That's equal to just j omega mu times sigma plus j omega epsilon, correct?
Yes.
Now we would like sigma plus j omega epsilon. We've got alpha and beta. This is where it gets a little hairy. So if I take this and I squared it out, I would set it equal to j omega mu sigma minus omega squared mu epsilon. Just bear with me. Y'all follow me? I'm just doing the math. This would be right that way and that way. Come over here and square that out. Now I have alpha squared minus beta squared. And then it's plus 2j alpha beta will equal that stuff, right?
Yes.
All right, now, if you look here, this term, I don't know if he does it this way, that term is equal to this term. So I would say that, since it's a minus that, I would say beta squared minus alpha squared is equal to omega squared mu epsilon. Y'all agree with that?
Yes.
And now I can say that I have omega,
We have,
I don't have mu and epsilon.
so we have three variables and two equations.
You gotta assume, as far as I know, mu is mu naught here. Does he do that, by the way?
No, he just solves for beta, alpha, and then plugs it into the.
Yeah, but you
That's what
can't,
H is.
for the E field or H?
H is. Just
skips
finds
over.
beta here, just listen up to that. Finds beta, finds alpha, and then plugs it.
That's H though, not E. Didn't you say we needed E?
Yes.
Yeah.
Where, is this 30 or 31?
That's 30.
I mean, is that the one we're doing?
Because that's right, and then our beta's right.
He doesn't ask for E, does he?
He doesn't solve that.
It says it wants instantaneous E.
Instantaneous expression for E. But he
Where
does-
is it? That's H.
H.
So he doesn't even do it. He said, the only way you can get the E field is you have to say it's either, you have to give me an additional bit of information. He doesn't even do that. It's just H field there.
So if we had any of them, we could solve it. We could solve
If
it.
we assume mu is mu naught, we got it. All right? Because then if you've got that mu naught, just look. If that's mu naught, right?
And you can solve for epsilon and sigma.
Then if that's mu naught, is just mu naught, then you got epsilon right here. Right? Because you've got omega mu, then you can get epsilon. Once you get epsilon, you come back over here, and now you can get, once you get epsilon, you can get sigma that way. Basically, you have to have one of the, since we have three unknowns, two equations, you have to have one of them in order to solve it uniquely. And he doesn't even get the E field, he just gets the H field. That's how you get it. Do you have a question? All right, what's the next one? I'm sorry.
And the last one would be 230. I mean, I don't know why I said 5.31.
Okay. This is helping. Sorry, he didn't mean to ask. I think he meant the H field, but he gives you the E field. The H field we can give exactly, but if we don't have the intrinsic impedance, we can't. Or the value of mu, you can't get it. What's this one?
Given at some point distant from a source,
This is
Out of-
31?
yeah, at the origin, it's in free space. We've got E.
Go ahead.
We've got E of R comma T equals,
What's it? R comma T, go ahead.
yeah, it equals 8 cosine
A cosine
8.
8.
Sorry, I might have said that.
My bad. Go ahead.
8 cosine of 9 pi times 10 to the 6th t minus beta r in the A theta direction. Volts per meter. It says find the frequency, phase constant, and H.
Okay, I want to say one thing. That's not a real wave. That R is spherical. Any real propagating wave in spherical coordinates will have a 1 over R if it's a far field. This doesn't have 1 over R, does it? I promise you, it'll have a 1 over R dependence. It doesn't. I know that right away. This is a fake wave. But you should just as well put a Z there. Then it would be legit. It's positive R direction. Y'all follow me?
Yes.
Now, for this one, let's do it. He wants frequency, right?
Yep.
How do you get frequency? Anybody?
It'd be
2 pi W.
Yeah.
Everybody pay attention. The
Omega
only thing you need for frequency is identify omega. It's the coefficient of t, and divide that by 2 pi. So it's really going to be 9 halves times 10 to the 6th hertz. What's the next thing he wants? It's free space, right? Guys, be attentive here. It's free space. What is the velocity in free space?
C.
C. Every engineer should know this. 3 times 10 to the 8 meters per second. Well, if it is in free space, right? Regardless of what it is, it's omega over beta, correct, class?
Yep.
So we have omega. Omega is equal to 9 pi times 10 to the 6, and it's over beta. Can you all find beta? What is it?
Wouldn't it be 3 pi over 100?
It's 9 pi times 10 to the 6 over 3 times 10 to the 8th, isn't it?
Yeah.
So this is equal to 9 pi times 10 to the 6 over 3 times 10 to the 8th. And that's pi over, or it's actually 3 pi times 10 to the minus 2. You agree with that? Is that right? That's small.
Yeah, that's right.
All right, that'd be radians. What else does he ask for here?
He wants to find H field.
That's the E field?
Yeah.
How do we find the H field? Look, again, I want to just show you, I'm going to clue you on something. This is free space, right?
Yes.
Yeah.
All right. If it is in free space, what is the intrinsic impedance?
Sigma would be 0.
It'd be
So-
mu over E square root.
It's eta naught, or it's 120 pi ohms, right? 277 ohms. That's nice because in your circuits problems, they always use 60 hertz, and you get 377 there too for a constant, 2 pi times f, right? So that's 120 ohms. Now, here's the beautiful thing about this. Which way is this wave propagating? I want you to just listen to me.
AR.
It's in the positive R direction, right? Positive AR propagation, right?
Yes.
Now, you can go and do this. This is so beautiful. This is really legit because that's not a real wave, but I can say the E field right there can be rendered as simply magnitude, which is it's in free space, it's e to the minus j beta. I'm going to leave it as just beta. We got beta ready. Beta r, and it's in the a theta direction. That would be the phasor form of what I just, yeah.
Oh, wait, yeah. No, that makes sense.
You with me, everyone? Take a second. I don't want to lose you on this one, right? And just remember, that's fake. Because you can't have a wave like that in spherical coordinates. It would have a 1 over r of dependence if it was a propagating wave. Now, if I want the H field, you remember when I showed you those equations on 372?
Yep.
1 over eta, unit vector in direction propagation, crossed into the E field, right? Remember that? All right, free space, what's eta?
120 pi.
Right, and so we have 1 over 120 pi. What's the unit vector in direction propagation?
It's going in the AR direction.
AR, right? The unit vector means it's got a magnitude 1, so it's AR crossed into the E field.
8 theta.
There's the E field right there, which is 8 e to the minus j. We've got beta already, r a theta. This is spherical. So I have 8, magnitude is going to be 8 over 120 pi. Then I have AR crossed A theta.
Is that minus A phi?
And remember, what was it? It was R. Now if you think about the coordinate system in spherical coordinates, let's see. So
Look at R phi theta, so it's
R cross theta is phi. It's hard for me to do.
So it's R.
Is it
R
minus
theta
phi? Is it minus phi though?
R theta phi, isn't it?
I thought phi was.
I have no idea. I always mix them up. I know which ones that they represent. I just don't know what order they go in.
If you think radially outward, R theta is downward, phi is in this direction. It's hard for me to draw it, but I sent you the coordinate systems. Just think R is always radially away. Just follow me, right? This is the direction. R is radially away. So AR
Yeah, it's R theta.
cross A phi. Phi is the
Yeah.
measurement from the z-axis on this plane, the vertical plane, R cos theta is phi goes zipping around counterclockwise, looking down the z-axis.
What is our theta?
So this is going to be what? R cross theta is a phi, right?
Yep.
And then it's going to be e to the minus j beta r, and that would be amps per meter. Is that what he has?
That's pi over 15. So 8 over 25
Yeah,
pi over
yeah.
15.
What does he have? Hang on. Is that right?
I think he does the simplification.
Well, just take, if you divide by, let's see, 4 over 60, 2
Yes,
over 30, 1
that's it.
over 15 pi.
That's it.
Okay. Y'all with me, class?
Yep.
You see the way I like using these tricks.
Yeah, he just made it decimals.
Okay. All right. I'm going to, for Wednesday, I'm going to give you,
Can we leave it in the phasor domain, or does it matter?
well, if he wants the time,
It just depends on whatever the questions ask, really.
Yeah, if he wants the time, you're going to take that magnitude cosine of omega t minus beta r.
Like on a quiz, would you care either way?
I would
Depending on, you would
If I
specify.
want time or,
If you didn't specify, it wouldn't matter. We could just do what we
Okay,
want.
well, then it doesn't matter. Okay.
I'm after magnitude most of the time, but I may want the phasor representation. Okay. All right, guys, see you on Wednesday. I'm going to give you some homework, and we're going to move into Chapter 6. Most of the stuff in Chapter 5 is just nauseating, curl this and cross that. It's easier to get right into 6 and do this stuff easy.
Are we going to have a review day?
Yeah, now